Well, we're going to look at limits and continuity of functions of several variables. This might seem very much to you like we're returning to Calculus 1.
And?
Well, only difference is, now we're going to have more than just functions of one variable, but functions of two.
I don't understand.
Well, you don't necessarily have to understand at the beginning, but hopefully you will by the end.
And?
Well, yeah, well, I hope you get it, but, well, give it a try. So, you see the expression, a delta neighborhood of a point in R squared. That is unusual, and that will come up in our chapter on functions of more than one variable, because R squared is where the domain of a function of two variables lives, not just on the x-axis, but in the entire xy plane. So, usually in reference to a disk of radius delta centered at the point. This is a two-dimensional version of an interval. Remember when Calc 1 you might have looked at absolute value of x minus x0 less than delta. Doesn't that sound somewhat familiar? And maybe then we would say absolute value of f of x minus some limit L is less than epsilon. So anyway, as one-dimensional intervals can be open or closed, just like this one is open and this one is closed. Of course, the significator is the round bracket means it's open, and the square bracket on this one means it's closed. Points are referred to as being in the interior of a neighborhood. For instance, 0 is in the interior of this one. The exterior of the neighborhood, for example, 5 is in the exterior of this one and this one. By the way, 0 is in the interior of this one also. Or on the boundary, okay, 4 and negative 1 are on the boundary for this one, and 4 and negative 1 are on the boundary for this one. Interestingly, though, there's difference. 4 is actually not in that interval, and neither is negative 1, but 4 is, and so is negative 1, part of this closed interval. So if a neighborhood doesn't contain any of its boundary points, then it's called open. If it contains all of its boundary points, then it is closed. So for functions of a single variable, this should be familiar. Limit as x approaches x sub 0 of f of x equals L. Means that f of x could be made arbitrarily close to L by making x closer to x sub 0. If we examine the function of two variables, f of x, y, in this expression, we can say limit as the point x, y approaches a limiting point x sub 0, y sub 0, then f of x, y approaches some number L. Now that is different. But that means f of x, y can be made arbitrarily close to this limit L by making the point x, y arbitrarily close to the point x sub 0, y sub 0. And the next definition will make that formal. So, definition, let f be a function of two variables, and suppose f is defined at each point in some circular region, sometimes we call it a disk, centered at the point x sub 0, y sub 0. Then we can write this. We can write limit as xy approaches the center of that disk, x sub 0, y sub 0, of f of xy equals L, means whenever we're given an epsilon, positive epsilon, we can find a positive delta such that f of xy satisfies the limit of f of xy minus L in absolute value is less than epsilon. In other words, f of xy is within epsilon units of L, the limit, whenever the distance between xy and x sub 0, y sub 0 satisfies, okay, now this is tricky, 0 less than this expression less than delta. So it's a little bit more than like the two-dimensional variation of a limit, which is way back up here, is a little bit more than that. So we're now saying, and I don't know if you recognize this expression here with the radical. I'm trying to get just the radical there. Do you recognize this expression? I hope you do. What it is, it's the distance formula applied to these 2 points. So whenever our point xy is arbitrarily close to x sub 0, y sub 0, then there's a number epsilon, or f of xy is within epsilon units of L. So that's the concept of a limit of function of two variables, and all the properties of limits from chapter 1 will still hold. We can go back into those if you want. Take the time if you want to look through properties of limits, look it up in your appendix or something like that. But anyway, here's some simple problems. Find the limits given. Limit as xy approaches the point x is 2, y is negative 2, of the expression 5xy squared over x squared plus y squared. So what do? X goes to 2, there it is, that'll be a 2. Y goes to negative 2, so this will be a negative 2, this will be a negative 2. By the way, this x would also be 2. So what we have 10 times 4, so 40 in the numerator, and we've got 4 plus 4, 8 in the denominator, so hopefully you see that that comes out to be 5. And that's pretty easy. I hope I did my arithmetic rightly on that. Let me double check that. 5 times 2 is 10, times 4 is 40, okay? And downstairs we've got 4 plus 4, so 4 plus 4 is 8, 40 over 8 is 5. Sure enough, this limit is 5. Here's another one. What's the limit as xy approaches, x approaches pi over 4, y approaches 2? Well, that's really interesting. So y approaches 2, we'd put a 2 in there for y. We'd put pi over 4 in for x, so pi over 4 times 2, which is pi over 2, so we'd have 2 times sine of pi over 2, which is 2 times 1. So this whole thing is equal to 2. That's pretty straightforward. All we had to do was substitute our values. So in Calculus 1, you sometimes saw when a limit didn't exist, it was often from a function being undefined at a point, or else having a left-hand limit not equal to the right-hand limit. I'll refresh your memory by showing you an example of one of those. Now, if we looked at the limit of x over absolute value of x, this is our function, our f of x, as x approaches 0 from the positive side, then we have a positive here over a positive, right? And a positive over a positive, of course, gives you a positive, but x over x gives you 1. So from approaching from the right to 0, this is equal to 1. Approaching from the left, however, this x is a negative. So x over x, of course, is 1, but it's really negative x over x. That makes this one negative 1. So at 0, well, what is it? Is it 1 or is it negative 1? The answer is it's neither, because that limit doesn't exist. And I think I have a picture of it here. Here's what it looks like in a graph. I cannot make my software not connect this point and this point, but really, if I could draw perfectly, a hole would be here, and a hole would be here, and none of this red stuff on that y-axis would be drawn. So there's an example of a function having a limit that does not exist at 0. With functions of more than one variable, the limit will not exist at a point if the limit is different on different paths to that point. And we'll look at an example in the next video.